Happy Wednesday. Couple of things before we get started. First off, this video is going to go relatively fast. So if you need to, that's why you're on individual devices, so that you can pause it, write stuff down, back up if you missed something, etc. So this video will be posted on Canvas throughout the entirety of this chapter. So if you miss something today in class, in the 2 mods of class that you have, you can always go back to it and fill in the first few pages of your note packet. Side note, when you came in, you should have grabbed a white note packet. That's the note packet for this next whole section, so that you have all of that stuff that we have. Okay? That's the first one. On second one, you have a test tomorrow in class covering 5.3 to 5.6. Okay? We are collecting from everyone the 4 purples, the 4 worksheets, and the 2 formatives. Now, if you've gotten a perfect score on your formative, you don't need to turn that back in. We've got it recorded. Okay? All right? So those 4 purples and the 2 formatives are on green. Those need to be turned in by tomorrow. Okay? All right. So here we go. Buckle up. Remember, you can always pause. Okay? So chapter 6 is going to start out with vectors in a plane. We're going to use vectors to represent quantities that have both magnitude and direction. Now, if that sounds familiar to you, I'm going to show you where that memory is from.
I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh, yeah!
So what Vector said there was that like I just said, we're creating quantities that have both magnitude and direction. Okay? So in general, a vector is a directed line segment with its tail at the origin and its head at the point A, B. So a vector would look like it would have a tail, and then it would have an arrow on one end. It is an arrow. It's a ray. It's not a line. No. It is a ray. So that this is here, then this would be the tail. That would be at the origin. And this would be the head. The arrowhead would be at the point A, B. And that would have then, that would be your directed line segment. So vectors are written in this way. We have some kind of a name. Usually that name is one of the letters. Okay? Then it is written the component form. Now notice those are not parentheses. They're not brackets. They are kind of like just things like that. I mean, it's just, I don't even know what you want to call that. Okay? Less than and greater than symbols for lack of a better term. Okay? The magnitude of the vector is going to be that vector's length. So the length from the origin here, in this particular case, from the tail, if you will, to the head, that's the magnitude. The direction of that vector is going to be unit circle direction. So this is going to be vector A, B, and then the direction here is going to be our theta, and that's going to be a unit circle, regular unit circle. 0 is straight out to the right, positive angles go counterclockwise. Okay? Now, names, again, could be single letters or they could be 2 letters if you're going between 2 points. And we write that with a little half vector, or if you wanted to put a full arrowhead on the top, that would be fine. That would be the way that you would write vectors in another method. If you were going from point P to point Q. Same thing. Yeah. Head minus the tail rule. Any 2 arrows with the same length and pointing in the same direction represent the exact same vector. Okay? Now, we can figure that out by doing head minus tail. Okay? So these are the same vectors, provided that they both have the same component form of their vectors. So if I do head minus tail, I'm going to take x of the head minus the tail of the, or excuse me, minus the x of the tail. So -1 minus -4 is going to be the x component of this one, and then 6 minus 2. Well, -1 minus -4 is +3. 6 minus 2 is 4. So the component form of vector RS is 3, 4. Now, for OP, O being here at the origin, 0, 0, if we have OP, then we can go directly to its component form, because that's just the coordinates then of point P, where the head is. That only works if your tail is at the origin. If your tail isn't at the origin, then you got to subtract the x's, subtract the y's, head minus tail for both. Okay? And because these two right here are the same, it is the same vector. Oops. Okay. Showing that RS is equivalent to PQ. Again, this would be head minus tail. Pause the video here. Show me that they're equivalent using head minus tail, and then restart the video once you have it, and they will be on there. So we have RS, head minus tail. So head is S, tail is R, because S is at the head side of the arrow. So this is going to be -1 minus -4, and 6 minus, oops, not a comma, correction, sorry about that, 6 minus 2. So that's going to be 3, 4, once again, for vector RS. PQ, so we would have Q minus P, so we would have 5 minus 2, and 3 minus -1. 5 minus 2 is 3. 3 minus -1 is 4. So this is vector PQ. They are the same. So we have just shown that they're equivalent because the component form of their vectors is the same. If their component form is not the same, then they are not equivalent vectors. They may be equal in magnitude, but they wouldn't have the exact same direction. Next up, we have, suppose that vector u is the vector -2, 5. That would mean then that vector u would start at the origin. It would have we would go negative to the point -2, 2, 3, 4, and 5. So there would be the point, the end, or the head of it. So this would be vector u. Vector v is 3, -2. So this would be vector v right there. We want to know where vector u plus v is. Now we can do this in one of two ways. The first way is we can just simply add the two component forms of this vector. So we would have -2 plus 3 and 5 plus -2. So u plus v then would be -2 plus 3 is 1. 5 plus -2 is 3. So the component form of u plus v, or the vector u plus v, would be 1, 3. That's the first way, mathematical way, totally doable. Second way is you can take vector v, which is right there, and you can move it to the tail, or move the tail of vector v to the head of vector u, and now you see that it ends at the point, oops, excuse me, wrong one, I used purple already. It ends at this point right here, which is the point 1, 3. So the component form of vector u plus v would be there. Those are the two ways that you can add vectors. Next one. Suppose vector v is, once again, 3, -2. So there is vector v. Well, we want to know what 3v is. Well, we would have 3 v's in there, all going in the same direction. So the next one that we would add would be right here. So this would be my second v. Here would be my third v. So all told, that would get me, this whole thing right here would get me vector 3v, or simply what I could just do is multiply, correction, I could multiply the component form each by 3, which would give me 9, -6. Oops, I put a parentheses. Bad, Lensmeyer. Got ahead of myself. There's the component form. That's not a bad one. There's the component form. And this is the point 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6. So this is 9, -6. Right there. That's how we get those. What about subtraction of vectors? So again, if we have vector u at -2, 5, so there is u, and we have vector v at 3, -2, then u minus v, that vector, is the same as vector u plus the opposite of v. Well, the opposite of v, I'll put that in green, would be right there. Notice how it is the same magnitude, it's the same length, it just is in the opposite direction. So the angle difference between them is 180 degrees. it is going completely back the opposite way. Now from there, we could go head to tail with it, and there would be where our point is. Oops, excuse me. Right there. Mathematically wise, what we could do is we could say that this is -2 minus 3, just subtract the component forms, and 5 minus -2, which then would give us the component form of u minus v would be -5, 7, which is what that blue dot, the blue point on that graph would represent. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. One of the things that we can do is we can do a machine gun, if you will, a rapid fire, if you will, of the vectors. So given those two vectors, given that r is 2, t is -3, well, what is u plus v? Well, u plus v is going to be -1 plus 2, 3 plus -5. So that's going to be 1, -2 will be the resultant vector. Okay. U minus v is going to be -1 minus 2 and 3 minus -5. So that's going to be -3, 8. T times u is going to be -3 times the vector of u would be -1, 3. So that would be +3, -9. Just distribute that in to both of those. RV plus TU, that's going to be, well, RV would be 2 times vector 2, -5, plus T would be -3 times the vector -1, 3. So that would then be 4, -10, and 3, -9. So that would be, let me get down here just a little bit. So then that would be the vector 7, -19. -r times u, -r would be -2, vector u would be -1 and 3. So then this one, whoops, that breaks. I don't know why that did that. It was the same stylus. This would be 2, -6. Now, when we're finding the vector quantities of a vector, so for instance, the magnitude and the direction angle, those are the two vector quantities. Okay? So the first thing, the magnitude, remember, is the length of the vector, and its symbol is a double absolute value. So for instance, this would be the length of magnitude, or excuse me, the magnitude of vector W would be a double absolute value with the W in the middle. Okay? So if we think back to the distance formula, if I've got a point and the origin, so if I've got a point A, B, and the origin, I want to find that distance. The distance is going to be the square root of a squared plus b squared. Okay? Well, that comes from the fact that if we were to make this right triangle here, this distance would be a, this distance here would be b. It's a right triangle, so it's the Pythagorean theorem. A squared plus b squared equals c squared. So c is equal to the square root of a squared plus b squared. Okay? That holds here in magnitude. So the magnitude, if we have the vector x comma y, then we'll call this, let's call this vector v. If we have that vector, then the magnitude of v is going to be the square root of x squared plus y squared. So if vector w is negative 2 comma 3, then the magnitude of w would be the square root of negative 2 squared plus 3 squared. Negative 2 squared is 4. 3 squared is 9. Add them together and we get the square root of 13. So that then is the magnitude of w. Preferably, we're going to leave those in simplified radical form unless told otherwise. Then, to find the direction angle of w, well, this now is going to be the trig angle. So just like when we were finding the angle through a point or given a certain point, what was the back first semester we were doing this, okay? This is going to be, we're going to use our reference angles. So the reference angle, theta prime, is going to be the inverse tangent of y divided by x. And remembering that we are going to drop any and all negative signs from x and y. So again, if my angle, my vector v is of the component form x comma y, we would do that. We would drop any negative signs. We would find the inverse tangent of that. And then on top of that, we would have our 4 quadrants. Well, in quadrant number 1, theta is my reference angle. In quadrant number 2, theta is 180 degrees minus my reference angle. In quadrant number 3, theta, my direction angle, is 180 degrees plus my reference angle. And in quadrant number 4, theta is 360 degrees minus my reference angle. Okay. So if we have vector w, once again, is negative 2 comma 3, the reference angle then, I would use theta prime, would be the inverse tangent of 3 divided by 2. I would drop the negative off of the negative 2, and that's going to give me an angle of 56.31 degrees and change. I round it. Okay? Because negative 2 comma 3 is a vector in quadrant number 2, then that means that my actual direction angle theta is going to be 180 degrees minus my reference angle of 56.31 degrees. So my actual theta, my actual direction angle, is going to be 123.69 degrees. So W is a vector that is the square root of 13 units long, and it has a direction angle of 123.69 degrees on the unit circle. Here's some more examples of vectors. We need to find the length, the magnitude of u, and the direction of vector u. So once again, here we go. Let's do magnitude first. Magnitude of u is going to be the square root of 1 squared plus negative square root of 3 squared. 1 squared is 1. Negative square root of 3, quantity squared, is 3. Square root of that is going to be the square root of 4, so that is 2. So the magnitude is 2. The length of that vector is 2 units long. Then we got to find the direction angle. So that's going to be the reference angle is going to be the inverse tangent of the square root of 3 over 1. Well, the square root of 3 over 1, inverse tangent, dropping the negative signs. That's going to put me at 60 degrees when I type that into my calculator. Because this angle, or this vector, this vector lies in the 4th quadrant. 1, negative square root of 3. Let me redo that for you because that just doesn't look good at all. Fourth quadrant, that's going to be 360. Actual theta is going to be 360 degrees minus 60 degrees. So my direction angle of u is going to be 300 degrees, and the magnitude of u is going to be 2. Now, if you're given the magnitude and the direction angle of v, then in general, vector v would be in component form the magnitude of v times the cosine of the direction of v, comma, the magnitude of v times the sine of the direction of v. That would be the general form of that. So if you're given the fact that you have this scenario, we could just go with 6 times the cosine of 135 degrees, 6 times the sine of 135 degrees, which is going to give me, this one is going to be negative square root of 2 over 2. This one is going to be positive square root of 2 over 2. So magnitude, or vector v, would be negative 3 square roots of 2, comma, positive 3 square roots of 2 in component. Last slide, find the component form of given the component form, of V, find the magnitude and the direction angle. Okay. So, once again, magnitude, -3 quantity squared, -4 quantity squared, and the big square root thereof. So that's going to be 9 plus 16, which is going to be 25. So that's going to be 5. Okay. Reference angle, inverse tangent of 4/3, dropping both of those negative signs. Punching that in on the calculator, I get 53.13 degrees. Being that this vector is in quadrant number 3, that would be then theta is going to equal 180 degrees plus my reference angle. So I've got a magnitude of 5, and I've got a direction of 33. Sorry, I can't do math all of a sudden. 233.13 degrees. Last concept for the day is now we want to find the unit vector. So a unit vector is in the same direction as any vector that we want, but it only has a magnitude of 1. Okay? So if you have the direction angle, which we have the direction angle for vector V, it's right here, is my direction angle. We know that the magnitude is 1. Come on down for me. There we go. So we can then say that, remembering that we'll call it the UV, the unit vector of it would be the magnitude is 1. The direction angle is 233.13 degrees. Magnitude is 1. Direction angle is 233.13 degrees. We can find it that way. Okay? So my unit vector here, which is a vector in the same direction as vector V from the problem above, but now it only has a magnitude of 1. If I type in 1 times the cosine of 233.13 degrees, I get negative 0.6. If I type in 1 times the sine of 233.13 degrees, I get a vector, I get an answer of negative 0.8. And so that would be the unit vector. It would be on the same path as, so here would be vector V, but that's 5 long. Vector, the unit vector would only have a length of 1. It would only be, basically you're finding the spot where it's going to meet up with the unit circle. That gives you, that's a whole 34 minutes so far of time frame. Again, if you didn't finish this video, make sure that you finish it at some point in time prior to Friday's class. Good luck on your test tomorrow.